All right, so we're going to talk about experiments and observational studies today. So in an observational study, researchers don't assign choices, they simply observe them. The text example looked at the relationship between music education and grades. In other words, if you take a music class, does it make you smarter or get better grades? Since the researchers did not assign students to get music education, and simply observed students in the wild, so to speak, it was an observational study. Because researchers in the text example first identified subjects who studied music and then collected data on their past grades, this was a retrospective study. You go back and look at things, look at data. Had the researchers identified subjects in advance, the collected data as events unfolded, the study would have been a prospective, right? Prospective. But, it's like you guys are in high school, right? Well, if I go back, when does band start here? 5th grade, something like that? If I go back and look at your records starting at the 5th grade up till today, that would be retrospective. But if I started with a bunch of 5th graders and they were in band or music or choir or whatever, and then I watched them, then it would be a prospective. Okay. Observational studies are valuable for discovering trends and possible relationships. However, it is not possible for observational studies. However, it is not possible for observational studies, whether prospective or retrospective, to demonstrate a causal relationship. And this is just statistics in general, right? You can see connections, but it doesn't mean that one thing causes the other. And we've gone over several examples of that. An experiment, in other words, listening to music or studying music doesn't necessarily mean it's going to have an impact on your grade. You can find a relationship mathematically, but it doesn't mean that it causes that. All right? So an experiment is a study design that allows us to prove a cause and effect relationship. Now, this is something completely different. This is usually scientific in nature. If I heat something up, when will it melt? Okay, I can predict when it will melt, but the data will confirm it. What happens if I heat up more of the stuff? Will the temperature be the same? What happens if I change the pressure? What happens if I do this? That's a different scenario. So in an experiment, the experiment must identify at least one explanatory variable called a factor to manipulate and at least one response variable to measure. Now, the key to a successful experiment is to isolate the parameters. I don't want to change 5 different things and see if it makes a difference. I want to change one factor at a time and see if it makes a difference. I'll give you an example. Mr. Adams last year was mentoring a robotics team, and we were trying to shoot these big foam balls through a hole, almost like basketball, and we weren't able to fire these projectiles consistently. So we tried to make some improvements on that, but the problem was we'd improve 5 different things at once, and we couldn't really tell what was actually making an improvement or not making an improvement. So I suggested that we do one thing at a time. So an experiment manipulates factor levels to create treatments, randomly assigns subjects to these treatment levels, compares the responses of the subject groups across treatment levels. In an experiment, the experimenter actively and deliberately manipulates the factors to control the details of the possible treatments and assigns the subjects to those treatments at random. So if I go back to my example of this robot that's shooting balls through a hole, we played around with the RPMs of the motors on the shooter to see what would happen. Specifically, when the ball goes through the shooter, the RPMs of the motor drop down a little bit, and we tweak some things to try and keep that speed consistent. Okay, so that would be a treatment that we applied. The experimenter then observes the response variable and compares responses in different groups of subjects who have been treated differently. In general, The individuals on whom or which we experiment on is called the experimental units. When humans are involved, they are commonly referred to as subjects or participants. The specific values that the experimenter chooses for a factor are called levels of the factor, and a treatment is a combination of specific levels from all the factors that an experimental unit receives. So if I go back to a robot shooting a ball, we did a bunch of things to try and to avoid a dip or an acceptable dip in the RPMs of the shooter motor. We ramped up the speed, we slowed down the speed, we changed a few things around, and then we looked at the data to see what was the most consistent. Control. We control sources of variation other than the factors we are testing by making conditions as similar as possible for all the other treatments. So what we did at first, we were shooting the ball from various locations at various angles, and I suggested, hey, let's just shoot the ball here at the same angle, at the same speed, and see what happens when we manipulate the speed or the RPM of the motor. Randomization allows us to equalize the effects of unknown and uncontrollable variations or sources of variation. It does not eliminate the effects of these sources, but it spreads them out across the treatment's levels so that we can see past them. Without randomization, you do not have a valid experiment and will not be able to use a powerful method of statistics to draw conclusions. So when it wasn't quite as random as you would like, but the randomization that we used could be the speed, speed it up a little bit, slow it down. We also changed the balls that we were shooting and to see if that made a difference overall. Replicate. So repeat an experiment applying the treatments to a number of subjects. Later this year, we will learn how our sample size helps us calculate how precisely our statistic estimates the true parameter. So if I go back to this robot thing, we manipulated the RPMs with one particular ball and saw that it worked well, and then we changed and put a different ball in there, and guess what happened? Not the same results. Well, I can't pick and choose when this robot is on the field what type of Nerf ball it's going to pick up and throw. So we had to figure out a way to make it better across the board. Those are some things that we had to talk about. So replication's the key. On all my research that I do at Notre Dame and Northwestern, I usually start off by replicating an experiment that's already been done by someone else. And then once I'm able to replicate it, then we tweak the parameters, usually one specifically, to see what happens. We will learn how to calculate the margin of error, just like the ones you read about in the newspaper, plus or minus 3%. Okay. The 4 principles of experimental design is what we're talking about. So control is the first one, randomization is the second one, replication is the third, and the last one is block. Sometimes attributes of the experimental units that we are not studying and that we can't control may nevertheless affect the outcomes of the experiment. If we group similar individuals together, then we can randomize within these blocks. We can remove much of the variability due to the difference among the blocks. Blocking is an important compromise between randomization and control, but unlike the first 3 principles, it is not required for the experimental design. We did this with the robot that I keep referring to. We used brand new Nerf balls, old Nerf balls. We looked at the size, we weighed them, we checked to see how much they would compress, and we were trying to figure out, but we ran experiments with the new Nerf balls. Then we ran experiments with the old Nerf balls. Then we randomized the Nerf balls, each time trying to tweak the parameters to get an overall consistency and accuracy as to where things were shooting. We also found out that the battery, as the voltage of the battery started to go down, that had an impact on the shooting. So diagrams of experiments can be helpful. It's often helpful to diagram the procedure of an experiment. The following diagram emphasizes the random allocation of subjects to treatment groups, the separate treatments applied to these groups, and the ultimate comparison of the results. So you got group 1 with one treatment, group 2 with a similar, or a different treatment because it's a different group. And then you compare what the difference was. And one thing I will say is that the head coach did a phenomenal job of collecting data and organizing the different groups so that we could look at the numbers. There were times where we thought that the results were way off base, but when you looked at the numbers, they were fairly consistent. It was just a different look or feel. How large do the differences need to be to say that there is a difference in the treatments? Differences that are larger than we'd get just from the randomization alone is called statistically significant. We'll talk more about statistical significance later on. For now, though, the important point is that a difference is statistically significant if we don't believe that it's likely to have occurred only by chance. One thing I'll say, if I go back to this robot shooting the Nerf balls on a target, sometimes we'd have a perfect trial run. And we thought that we nailed it. And then we'd run another trial run, and it wasn't perfect. So we tried to figure out why it was perfect that one time, and the next time it wasn't. But both experiments and sample surveys use randomization to get unbiased data. But they do so in different ways and for different purposes. The sample surveys attempt to randomly select participants from the population. Experiments are usually done with a pool of volunteers, which can create its own set of difficulties. But we randomly assign the treatments to our volunteers to reduce bias. So controlled treatments, often we can compare a situation involving a specific treatment to the status quo situation. A baseline or business as usual measurement is called a controlled treatment, and the experimental units of whom it is applied is called the control group. If we go back to Mr. Adams helping out at Notre Dame and Northwestern, like I said, the first thing I do is try to replicate an experiment that somebody else did, and that's the baseline. So they have parameters, they have an experiment that they've done. If I can replicate that experiment and I get the same results or the baseline or control treatment that they got, then when I go to tweak a parameter to see if there's a change, I can have a lot of confidence in that experiment. So you always start with a control group. Blinding. When we know the treatment was assigned, it's difficult not to let the knowledge influence our assessment of the response, even when we try to be careful. In order to avoid the bias that might result from knowing what treatment was assigned, we use blinding. There are two main classes of individuals who can affect the outcome of the experiment. Those who could influence the results, subjects, treatments, administrators, technicians, and those who evaluate the results, judges, treating physicians, so on and so forth. When all individuals in either one of these classes are blinded, the experiment is called single blind. So I want to test a pharmaceutical company's new drug that's supposed to fix something. If I tell everybody you're going to take this drug and it's going to make you feel better, it may have an impact on how they feel. So we give them a placebo. And they don't know if they're taking the drug or not, and then they're a little more, I don't want to say honest, but they're unbiased for sure. Whenever we have both classes blinded, then it's a double blind. That's where we give the placebo to one group and don't give it to the others, but even we don't know who has a placebo and who doesn't. And so then the results can later be identified. Somehow you have to keep track, because you want to know if it works or not. Often, simply applying any treatment can induce an improvement. To separate the effects of the treatment of interest, we can control the treatment that mimics the treatment itself. A fake treatment looks just like the real treatment, being tested, it's called a placebo. So we give somebody a pill, it's nothing. It's just salt. Then we give somebody a real pill that has the actual drugs in it. And even then, they think they're getting the pill to treat whatever they need treated, and then they believe that's called the placebo effect. But placebos are the best way to blind subjects from knowing whether they're receiving the treatment or not. The placebo effect occurs, as I was getting to, where the individual thinks they're getting the actual treatment and they believe that it's working. Placebo controls are so effective that you should use them as an essential tool for blinding whenever possible. So drug companies, pharmaceuticals do this all the time. So the best experiments are usually randomized, comparative, double-blind, a control group, either placebo or a standard treatment. Blocking, when the groups of experimental units are similar, it's often a good idea to gather them together in blocks. Blocking isolates the variability due to the differences between the blocks so that we can see the differences due to the treatments more clearly. We did a great job with that robot by blocking things. We had 3 brand new, fresh out of the package Nerf balls. We had 3 very old, very used Nerf balls. And so we blocked that way. When randomization occurs within the blocks, we call that a randomized block design. In our particular case, we tried to randomize. We had 3 brand new balls. Each ball was different. We labeled each one of the Nerf balls, N1, N2, N3, new 1, new 1, new 1, new 2, new 3. The old ones were 01, 02, 03, and then we collected the data on those individually as well. So here's where an experiment might look like for something. This is 12 tomatoes from store A and 6 from store B, and then we want to figure out some information. So block A has 12 tomato plants, block B has 6 tomato plants. So store A, store B, block A, block B. You have one group, treatment control, 4 plants, okay. What did they compare the juiciness and tastiness? Group 2, 4 plants, treatment 2, half a dose. You're comparing the juiciness and tastiness. Group 3, 4 plants, full treatment of the dose. So I don't know what the treatment is. I'm assuming it's to the plant, and then we're trying to see if it makes the plant juicier or tastier. Okay. Now you do the same thing with block B. Group 4, 2 plants, treatment control. Probably doesn't have any treatment at all. Group 5, 2 plants, half a dose, whatever it is. Maybe it's some sort of fertilizer. Group 6, 2 plants, full treatment. Then you compare the juiciness and tastiness of it. Blocks and treatments, we have to be careful when reading that previous diagram. We have only 3 treatment groups, not 6. Okay. What are the 3 treatment groups? No treatment or control, half treatment, and full dose. Our goal is to ensure that each treatment group will have 4 store A tomatoes and 2 store B tomatoes. This way we can isolate the effect of the fertilizer, guessed it, fertilizer, and eliminate any store A versus store B differences. In retrospective or prospective study, subjects are sometimes paired because they are similar in ways not under study. Matching subjects in this way can reduce variability in much of the same way as blocking. Blocking is the same idea for experiments as stratifying is for sampling. Both methods group together subjects that are similar and randomized within these groups as a way to remove unwanted variation. We use blocks to reduce variability so we can see the effect of the factors. We are not usually interested in studying the effects of the blocks themselves. Sometimes data comes out of that. So if you look at this chart, right, I got store A, store B. They grow plants, they use fertilizer. Well, the goal is, I think, if you look at this, The third treatment for either store A or store B should be a little tastier and a little juicier, right? Now that doesn't mean we're not comparing store A's juiciness to store B's. So we're isolating two different types of plants and the overall effect of the fertilizer. Although maybe store A has juicier plants than B. But we're not comparing that. Okay? And so we're trying to we're isolating variability, but at the same time we're focusing on factors and parameters that we're trying to control and manipulate. One AP tip, the AP rubrics require that blocking descriptions focus on the use of blocking to reduce variability within the treatments, not a discussion of comparing differences in the block groups. You may have variability in the block groups, but that's not the purpose of the experiment or the purpose of blocking. Adding more factors, it is often important to include multiple factors in the same experiment in order to examine what happens when the factor levels are applied in different combinations. So if I talk about the robot and us shooting that Nerf ball, the type of Nerf ball they had an impact on it. The battery voltage had an impact on me. The distance away from the target had an impact on it. The formulas that we used to calculate the RPMs had an impact on it. So we had lots of factors that had an impact on it. Our overall goal was to improve accuracy in our targeting. In this particular case, here's an example. The following diagram shows a study of effects of different fertilizer/water combinations on the juiciness and tastiness of tomato. So now they're adding another parameter. What happens with water? So they separate it into doses of the fertilizer with water and doses of the fertilizer without water. This would be something similar to like what Mr. Adams would do. First, I would do the experiment done by somebody else with the different doses of fertilizer. And then I would say, wonder what happens if I add extra water. And then I would compare the data. So we can add more factors once we get established. And that is really scientific research in a nutshell. Everything that you learn in your science classes is somebody has an idea, they start with an idea that's already kind of laid down the foundation, and they add an extra factor to it. Confounding. When the levels of one factor are associated with the levels of another factor, we say that these two factors are confounded. When we have confounded factors, we cannot separate out the effects of one factor from the effects of the other factor. In other words, in this experiment of the tomato plants, if I add more water and it's juicier, do we say it's juicier because of the water? Probably. But is it juicier because of the fertilizer? Probably, but I can't separate it because I added both. Okay? Confounding can arise in experiments when some other variables associated with the factor has an effect on the response variable. A confounding variable is a third variable that is unfortunately intertwined in our experiment. Our goal is to measure how the factor affects the response variable. But when another variable is intertwined with the factor, we can't tell how much each of these variables is affecting the response variable. We describe this problem as confounding. Okay, so at the end of the day, I want juicy, tasty tomatoes. And if I have a combination of fertilizer and water that works, I guess it doesn't really matter. So if I wanted to go out and make a lot of juicy, tasty tomatoes, I'm just going to stick to that combination of the fertilizer and water. Somebody could go out and see if you tweak the fertilizer a little bit, tweak the water a little bit, you can. But that's another experiment. Okay. So we wish to see if detergent A cleans better than detergent B. Detergent A is used in one washing machine and detergent B is used in a different washing machine. You see the problem there? At the end of the experiment, we have confounding. That is, we can't tell the difference in the cleanliness of the clothes, whether, if it's caused by the detergent or the quality of the machine that was used. Lurking variables. A variety of variables may be influencing a given situation. Sometimes isolating the effect of one variable may be difficult. there may be lurking variables that we need to think about. We sometimes discuss the potential effects of these other variables. So let's bounce back here, though. I didn't want to gloss over that too much. You could fix this experiment by just washing everything in one washing machine, right? But then again, even if I do that, does it help to determine the cleanliness or how clean the detergent gets it? I mean, you could compare A to B, I suppose. Or you could compare the washing machines, but anyways, that's just an example. So what can go wrong? Don't give up just because you can't run an experiment. If we can't perform an experiment, often an observational study is a good choice. Beware of confounding. Use randomization whenever possible to ensure that the factors not in your experiment are not confounded with your treatment levels. Be alert to confounding that cannot be avoided and report it along with your results. Just like all the other data, you have an outlier, do the calculations with the outlier, do the calculations without the outlier, but don't toss the outlier out. Same thing here. Conduct the experiment, collect the data, share the data with everybody else, let people make their own decisions. What we have learned, oh wait, I skipped a thing. Bad things can happen even to good experiments. Protect yourself by recording additional information. Don't spend your entire budget on the first run. Try a small pilot experiment before running a full-scale experiment. You may learn some things that help you on the full-scale experiment. Now, this is what Mr. Adams does when I work with Notre Dame or Northwestern. They have me come in and do the little teeny tiny trial thing. Then they look at the stuff that I do, and then they make a decision. Do they plow forward with it? Okay. Often we do discover a lot of things in that little trial run, like a lot of stuff. Nothing ever works out exactly how you think. You'll discover all kinds of crazy stuff in those small trial runs. What we have learned, we can recognize sample surveys, observational studies, and randomized comparative experiments. These methods collect data in different ways and lead us to different conclusions. We can identify retrospective and prospective observational studies and understand the advantages and disadvantages of each. Only well-designed experiments can allow us to reach cause and effects conclusions. We manipulate levels of treatments to see if the factor we have identified produces changes in our response variable. I just thought of something as I was going over this. You know, this laundry detergent washing machine thing is a big deal, right? So if I manufacture laundry detergent and I use one washing machine and it works phenomenal in that washing machine, there could be something in that washing machine that works great with my detergent. So I do have to introduce some randomization, different washing machines. So there's a balance, I guess is what I'm saying. So keep that in mind. Our overall goal is to collect data and try to improve based on the data or make predictions or compare. We basically look at the data and try to interpret what the data means. We know the principles of experimental design. You identify and control as many sources of the variability as possible. You try to equalize the many possible sources of variability that cannot be identified by randomly assigning experimental units to treatments. Replicate the experiment as many subjects as possible, or on as many subjects as possible. Control the sources of variability when we can. You can consider blocking, that can be helpful, but even then, we recognize but cannot control everything, right? What have we learned? We've learned that the value of having a control group and using blinding and placebo controls. We can recognize problems posed, confounding variables in experiments, and lurking variables in observational studies. On the AP exam, you need to think about a couple things. As with stratification, make sure to justify your choices of blocks according to the parameter of interest. So, let you in on a secret, you're going to have to design an experiment on the AP exam, and you're going to have to go through this whole process. These are the tips as to how you demonstrate your knowledge of experimental design, whether it be an experiment or observational study. Blocks are to ensure the variability is reduced across the treatment groups, not to create more groups to compare. Write specifically and in detail. Usually one of the 6 multiple choice questions is focused on survey or experimental design. So, and we'll talk about the different questions and the breakdowns of the questions. But there are 6 multiple choice questions. Usually one of them is on experimental design or survey design. Don't be confused by double blinding. There is an assistant who sets up the medications and the code for each treatment. Someone knows who is receiving each treatment, but the subjects and the administrators and examiners won't know during the course of the experiment. Okay, so obviously one person knows, or the experiment doesn't matter, but that person is sworn to secrecy and can't tell the administrators, can't tell the subjects. Okay. Remember that the surveys and the observational studies, we're collecting data, and we can only conclude that we have an association. With experiments, however, we can kind of confidently believe in causal conclusions. If I add more water and fertilizer, I get a juicier, tastier tomato. The key difference between a survey and an experiment is that in an experiment, we apply the treatment to the subject. A survey, we're just observing things, okay? If I take honor roll students or National Honor Society students and I observe their behaviors, I'm looking at a variety of parameters. I can hone in onto them, but I'm just collecting data, just observing. That's a survey or a study. If I say, I want to know if there is a cause or a causal relationship between the hours of doing homework and, GPA, then I could create an experiment and collect data. But that would also probably be a survey because I can't control. Well, I could though. Actually, I take it back. If I wanted to create an experiment, I could say, well, I believe that if you study twice as hard, it'll impact your GPA this much. And then I can actually do that. Force kids to study twice as hard. You study 20 hours, now you got to do 40. But that's kind of the gist of it. Okay? Any questions for Mr. Adams about this stuff? Whew, that was a lot.